So this was another example. Then now you can say, remember what I did is I make the matrix P by putting eigenvector 1, then eigenvector 2. So now someone can ask, so what about if you put the eigenvectors in a different order? What happens then? Because nobody tells you you have to put eigenvector 1, eigenvector 2. Why not eigenvector 2 and then eigenvector 1? No? Because the 1 and 2 are arbitrary. It's just the sequence how I find the eigenvectors. No? Okay, so I have another example which I make a little bit shorter, so I will not show you the calculation for finding the inverse, but I hope the next example makes it clear to you how the order of the eigenvectors affect the entries on the diagonal of your diagonalization. So one more example that will be very easy to find the eigenvector values. So another example, my matrix A, this time it's three-dimensional, 2, 0, 0, 3, negative 1, 0, negative 3, 0, 3. So that's a matrix, and the special thing about this matrix, it's lower triangular. So that means if you see this, if this matrix and someone asks you what are the eigenvalues, usually that's a complicated question. You have to find the characteristic equation. Here it's not. The eigenvalues are just along the diagonal. So the reason this is lower triangular. Same thing with upper triangular. In general, it's more complicated. So because the matrix is lower triangular, so we have right away the eigenvalues, lambda 1, and I just number them like this now. No? Lambda 1 is 2, lambda 2 is negative 1, and lambda 3 is 3. So 2, negative 1, 3. So now the eigenvalues here are free. We still have to find the eigenvectors. So, oh God, eigenvectors. So we have, we always solve lambda I minus A times X equal to 0. So let's say lambda, which ones do I start first? Let's say lambda 1. So I do 2 along the diagonal and subtract the matrix. So I have 2 minus 2 is 0, 0, 0, minus 3, 3, 0, minus 3, plus 3, 0, 2 minus 3 is negative 1, 0, 0, 0. So that's what I get here. And what you can, for example, do, you take this line, divide by negative 3, and then also flip at the same time. I like to make it short, so I divide by negative 3 and flip it with this. So, and yeah, actually, I should also flip this, but I do 2 steps. So if I divide by negative 3, I get 1, negative 1, 0, 0. Then the 0 comes down here. And I hope it's also okay, I at the same time add row 2. No? So I also eliminate this. So this plus this is 0, this plus this is 3, this plus this is negative 1 and 0. And then I divide by 3 and flip it with this. So we get 1, negative 1, 0, 0. 0, 1, negative 1/3, 0, 0, 0, 0, 0. And finally, we need to eliminate this one. This is row echelon form. So I add row 2. So I get 1, 0, minus 1/3, 0, 0, 1, minus 1/3, 0, 0, 0, 0, 0. Again, that we have here 0 row. That's what you need, otherwise you don't have an eigenvalue. Then otherwise there's a mistake. And from this we can actually find now our eigenvector. So let's say, again, if this is x, y, and c, c gets a parameter, so c is equal to t, then y is equal to 1/3 t, and x is equal to 1/3 t from here and here. So our solution looks like t times, so again, t and r. And then so solution looks like t times 1/3, 1/3, and 1. And if t is equal to 3, for example, then we have the first eigenvector is 1, 1, 3. So this is an eigenvector for 2. So if you multiply this by the matrix A, you get 2 times 1, 1, 3. So the next one is -1. So, and again, I write down my linear equation system, this one, here 0, 0, 0, and then I take -1 and subtract the matrix. -1 minus 2 is -3, 0, 0, -3, -1 plus 1 is 0, 0, 3, 0, -1 minus 3 is -4. Very nice. This is actually easier than the part 1. So, for example, I can divide this by -3, then I subtract row 1 and I add row 1. So if I divide this here by -3, I get 1, 0, 0. This minus this is 0, 0, 0, 0. This plus this is 0, 0, -4, 0. Then I divide by -4 and switch the 2. So I have 1, 0, 0, 0. 0, 0, 1, 0, 0, 0, 0, 0. Again, one rows, which is totally 0. Again, that's important, otherwise we have a mistake. And again, x, y, c. So this and this is now leading variables. So y get the parameter, y get equal to t, c is equal to 0, and x is equal to 0, and t is in R. So our solutions are t times 0, 1, 0. And now I can say t equal to 1. We get our second eigenvector is 0, 1, 0. So again, it's also obvious if I multiply this by the matrix, it becomes 0, minus 1, 0. So it's just the eigenvalue is -1. And so now, last thing, lambda 3 equal to 3. Same calculation again. 3 along the diagonal, and I subtract the matrix. So 3 minus 2 is 1, 0, 0, right-hand side 0. Then minus 3, 3 minus minus 1 is 4, 0, 0. Then 3, 0, 3 minus 3 is 0, 0. And again, very easy. So I add, sorry, what do I add? Add I add 3 times row 1, and I subtract 3 times row 1. So 1, 0, 0, 0. This plus 3 times this is 0. This plus 3 times this is 4, 0, 0. This minus 3 times this is 0, 0, 0, 0. Again, we have a 0 row. Otherwise, we have a mistake. And here, this 4 I can just turn into 1. So I divide by 4. We have 1, 0, 0. 0, 0, 1, 0, 0, 0, 0, 0, 0. So we have our reduced row echelon form back. So the non-leading one is this time the C. C gets a T, but there's zeros here, so X and Y are 0. So T and R for the solution. For the eigenvalues, again, T equal to 0 would not be allowed. So 0, 0, 1. And again, it's easy to take t equal to 1, and we have v3 equal to 0, 0, 1. So now this part of the question answer the question, what are the eigenvalues and what are possible eigenvectors? So we have this, this, and this. And this time now, we play a little bit around with how do we make the matrix P now? Again, to diagonalize A. But this time, we do several options. And I just tell you a few options and then see what will be the outcome if we diagonalize A with this matrix P, because there are different options for P. Okay, and again, sorry, I would like to have all this on one page so you can actually see it. Even this is not big enough for this. So I hope you have V1, V2, V3, and these are the eigenvectors. Maybe I should just copy it on the next page so we have everything together. So we have lambda 1 equal to 2, and V1, yeah, maybe that's better, is 1, 1, 3. Then we have lambda 2 equal to -1, and V2 is 0, 1, 0. And then we have lambda 3 equal to 3, and V3, the corresponding eigenvector, which we picked, was 0, 0, 1. Okay, so now the first, I actually here have on my list, I have 3 different versions of P. So the first version of P is 0, 1, 0, 1, 1, 3, 0, 0, -1. And obviously 0, 1, what did I do here? This is V2, this is V1, and that's really, why would I take 1? Okay, I'm not sure. I hope it's okay. If +1, then -1 works too. Yeah, sorry, because I actually prepared P inverse, I like to write -1. So my previous, I cannot tell you why in the world I would do this. But okay, in my example, I did. I picked T equal to -1, so we have a -1 here. Sorry. Why? Okay. Strange. Okay, I picked -1. So, and so we have -1, that's the eigenvector for us for 3. And this is V3. Then the reason why I said, why not just pick 1? Because I like to write P inverse, and okay, it would not be too complicated to change this, but I better don't. So this is -1, 1, 0, 1, 0, 0, 3, 0, -1. So if you have this matrix, you can find this inverse by doing the regular calculation. And then we calculate what is actually P inverse A P. We know this is a diagonal matrix. Okay, what I like to do is actually I give you 3 options. No, there's actually one more options and actually much more option, because you can arrange 3 vectors in 3 factorial 6 different ways. I just do 3 here. No? So another P would be 1, 1, 3, 0, 1, 0, 0, 0, -1. So again, what is this now? This is V1, that is V2, and that's V3. If you calculate the inverse, it's also just the permutation of these rows. So I have here 1, 0, 0, -1, 1, 0, and the last one doesn't change. And again, the question is now, what is this? We know it's a diagonal matrix because the columns of P are eigenvectors. Okay, and I have one more. I actually, again, don't really know why I picked these 3 and not the other 3. I just, yeah, did it. So 0, 0, -1, 0, 1, 0, 1, 1, 3. So again, this would be, this time this is V3, this is V2, and this is V1. Again, each time you see the columns are the eigenvectors. And again, the P inverse is just a permutation of the columns from here. So here we have 3, 0, -1, -1, 1, 0, 1, 0, 0. And again, we can calculate Okay, so I hope that was not so confusing, because for the reason I picked the -1 here, but okay. So if these are the eigenvectors, I can put them in different order to get my by transformation matrix P, because nobody says I have to put this first. I can put it second or third. No? And each time when I get a P, I get a P inverse. And you calculate it, and I hope I did this correct at home. Okay, now the question is, how does it affect the outcome of the diagonalization? So we know already each time we have only numbers along the diagonal. And my question is now, what are the numbers along the diagonal? Can someone tell me what would be in the first case? What would be the first, second, and third number? What would be the first number? Any idea? The first number has to be the eigenvalue for the first column. And what is the eigenvalue for the first column?
-1.
Yeah, this is -1. The second number is the eigenvalue for the second column, which would be, in our case, V1 is 2. And the third number is the eigenvalue for the third column, which would be 3. Yeah? Because that is, in the moment you fix in which order you write these eigenvalues, you fix the numbers in the diagonal, because it corresponds always to the eigenvalues of the corresponding column. Okay, so in the second row, what would be here along the diagonal? Starts with V1, so the first number is
2.
Eigenvalue for V1 is
2.
2. Then eigenvalue for V2 is
-1.
-1. And eigenvalue for V3 is
3.
3. And now the last one. Again, we get a diagonal matrix. That has to be because the columns of P are eigenvectors. But what diagonal you get depends on the order, how you order them. No? Okay, so what would be here? First diagonal element would be
3.
3. Second diagonal element would be
-1.
-1. And the third diagonal element would be
2.
2. And again, don't ask me why I picked these 3 there, because you have 3 eigenvectors, you have every 6 different options. No, I just picked these 3, and I don't really know why I picked these 3. But I hope this really shows you, because what about if you reorder them? What effect does it have? The effect is just you still get a diagonal matrix, just in a different ordering. No? Okay, so I hope this example clarifies for you what is the effect of if I calculate my eigenvectors in a different order, no? Because everyone can do it differently, no? And the result is actually always the same, just the numbers come in a different sequence, no? Okay, and the last thing is now about, I mentioned this word before, algebraic multiplicity. So for example, sometimes you have an eigenvalue and it's a double zero of your characteristic polynomial. Does it mean that they're also always, like if it's double, does it always mean they're also 2 different eigenvectors? No? So the last item in this section, which I cover after the break at the beginning, and then we are done with this section, is the difference between something we call the algebraic multiplicity and something which we call the geometric multiplicity. So even these kind of examples are always a little bit painful because you always have to calculate inverses. Also in the following, I think I also will just always tell you the inverse, which also makes it important that I look at my notes so I don't, because you can always do things in different ways, as you have seen. So otherwise I cannot tell you the inverse if I don't follow my own sequence. So after the break, we do more examples for finding eigenvalues and eigenvectors. And the point about the two examples after the break is to show you the difference between algebraic multiplicity and geometric multiplicity of an eigenvector. And then this finishes kind of our crash course into eigenvalues and eigenvectors. And then a little bit, I think for sure I cannot finish. I will start with section 6.1 after the break, after we finish two more examples. Okay, any more questions about this last item here? Otherwise, I would stop the video for a moment and then have a 10 minutes break. Are we okay with having a break?
Yes, we're all good.
Okay, then I stop sharing the screen and we continue around 20 minutes after 10.